In this video, we present a new body of research that we call transient rendering. It's presented by Adam Smith and James Skorupski. There is growing interest in time-of-flight-based computer vision applications, and we want some general physical explanation for the measurements we make. Our research contribution is a formal model that lets us do just that. Before we launch into our work, we would like to cover some background material. What we would like to borrow from other fields is a rigorous mathematical analysis, a simulation specific to light, and capturing of the transient effects, where transient is a notion we will define later. What's out there that's related to this is LiDAR, sonar, and the rendering equation. LiDAR, or light detection and ranging, similar to radar but for light, tends to be based on a very simple mathematical analysis that tends to only assume one or two bounces, reflection, and no transmission. The analysis is specific to light, and does capture the transient effects of light propagation. Sonar, or sound navigation and ranging, is similar to LiDAR, but focuses on the propagation of sound. Sonar models tend to have a rigorous mathematical analysis, taking into account many difficult-to-model effects such as diffraction and nonlinear effects of the media. These effects that it takes into account are not specific to light, therefore we cannot simply recycle these models. However, these models do give us a template for which to base our analysis of the transient effects on. The rendering equation, as introduced by Kajiya in 1986, provides a rigorous mathematical analysis of light as it bounces around in a scene, even after an infinite number of bounces. Its model is specific to light, taking into account models that we recycle in our own work, such as the bidirectional scattering function. The rendering equation, however, does not tell us about the transient effects of light. You can see the equation on the right as presented in the original paper. On the left, we sum it up in simple operator form. This statement simply says that the total light at every point in every direction is simply the light emitted at that point in direction, as well as a single bounce of the final light. Note that this relation is recursive. The left L depends on itself on the right. An important distinction in this work that we've mentioned so far that's critical for understanding what we've done is the distinction between steady state versus transient light transport. To illustrate this concept, here's a simple visualization. We have a scene with two triangles and two rays entering from the left. The rendering equation, the standard rendering equation, can tell us exactly where the light exits and how much energy it carries. And in this case, it tells us that all the energy is carried upwards. However, in the transient case, we can tell when the light came out. Here we can see that the top pulse exited the scene first. This detail was not given away by the steady-state solution. In the steady-state case, normally we reason about the energy of light passing through a certain point in a certain direction. This is equivalent to the number of photons received at that point, or the radiance of light outward from that point. However, in the transient case, we reason about the power as a function of time, otherwise measured as the rate that photons are received at that point, or the radiant flux through that point. In the steady-state case, we are reasoning about a function that's valid over all time. This is equivalent to saying that the propagation delay between 2 points is 0, corresponding to an infinite speed of light. However, in the transient case, we care about the speed of light being some constant instead of infinite. Note that in the expression on the right, if we were to put in infinity for c, we would simply reduce to the 0 that we have on the left. Put simply, the steady-state light is a function of point and direction, whereas the transient solution also depends on time. Here we present the transient rendering equation. This is our primary contribution. Stated in a form that's very similar to the operator form of the standard rendering equation, we can see that it says, translated into English, that the final flux as a function of time is the initial flux as a function of time plus the single bounce transport of the final flux. Note that this solution is recursive just as the original equation was. The global light transport operator G is the composition of two physical processes, propagation and scattering. Propagation is where all the transient effects live and depends on the speed of light. Scattering is the same as in traditional rendering. Here's an example of transient rendering in action. In the top part of our diagram, we can see a one-dimensional world with a horizontal axis being space for this world. It is comprised of an eye point E, a light point L, and two surfaces A and B, where A is partially transparent and B is opaque. The middle part of our diagram shows the result of transient rendering. We can see as a pulse of light at point L expands, it eventually touches point A, where part of it is transmitted and part of it is reflected. We continue propagating rays throughout the scene and tracking where they scatter to. At the bottom of our diagram, we can see a summary of the light that passes through the eye point E. To be clear, the inputs to this process were the positions of the eye, light, and surfaces, as well as information about how light scatters through the surfaces. Finally, we needed to know the initial light emission pattern. The output told us about the received light power at every point, at every direction, at every time. True to our motivation, we would like to have a way to explain sensor readings. We've developed a sensor model, which is too complex to present here, which takes into account several realistic cases and allows us to, given a model of the world and parameters of the sensor, generate a sequence of energy measurements which would be comparable to what we could pick up in a sensor that is possible to build. This work opens up several new research directions. Importantly, new applications which could not be done before, the area of building sensors to directly capture these transient patterns for further reasoning about them, as well as the direction of generalizing the theory and implementing it computationally. Some applications that we've unlocked that haven't been capable before are the following. 1, 3.0D range finding, or the recovery of hidden surfaces, goes beyond traditional 2.5D range finding, which only tells you about surfaces facing the eye point. Presumably, if we can reason about the way light bounces as a function of time, we begin to have a hope of reasoning about the back surfaces or the hidden ones that are not directly visible by the eye. Another application would be estimating subsurface scattering parameters from samples in time instead of space, allowing much higher resolution sampling of these parameters. And finally, a family of LiDAR applications based on a model-based approach using a much more complex model than traditionally used. In terms of building sensors, existing LiDAR hardware measures most of the data we need, but throws most of it away. In order to improve our theoretical analysis, we can generalize our model to include other natural phenomena, including wavelength-dependent dispersion, subsurface scattering, and phosphorescence, a distinctly transient effect normally ignored in graphics. In developing a computational implementation of our theory, it would be valuable to determine which parts of a scene a particular measurement depends on, explore functional representations, and augment a common ray tracer. In conclusion, we have taken initial steps into exploring the effects of light propagation delay and call this transient rendering. We hope that transient rendering can serve as a principled foundation for future time-of-flight-based computer vision techniques.